Okay, so welcome again. Today we have Sergio Romero from University of Göttingen and University of Malaga. So he is a joint PhD in both of these universities. So he will talk on topological and homological tools for the study of spaces from infinitely far away. So he will give 5 talks. So today is the first talk from the series where he will talk about motivation, groups as metric spaces. Yeah, over to you, Sergio.
Okay, thank you very much for the introduction. So I will now stop my video and share my screen. I want to talk to you about geometric group theory, as it is a good motivation for coarse geometry. So the idea in geometric group theory, this is going to be an introductory talk. It's not going to be a research talk. It's some crash course or introduction. The idea here is that if you're working with some group, if we're working with some group G, and we assume it is finitely generated, I have some algebraic objects. So I can see the group G as an algebraic object and do some algebra with it. Or we will see a way to see G as a metric space. So then we can also do geometry with the group. So the whole philosophy of this geometric group theory is that algebraic features, so algebraic features of the group will correspond to coarse geometric properties or features of G, seen as a metric space. So here coarse means that the only geometry we're going to see about G is by looking at the space from infinitely far away. Please feel free to interrupt me if you cannot see something, you cannot hear me well, or if you want me to repeat something. So let's start with this. We'll define how to induce this metric space. So now we consider any group G, a finitely generated group. Then it has some finite generating set. So let S be a finite generating set. We can assume S to be symmetric. So assume that S is symmetric. This means that if I take an inverse of an element of S, this is going to still be in S. I can always consider such generating set just by adding manually every inverse. So then we will define something that is the Cayley graph. So the Cayley graph is the following. Is a graph that depends on G and S, and the vertex set is the following. So the vertex set of gamma is the underlying set of G. So I consider the elements of G as vertices. And when do I have an edge? So if I have two different elements in G, then they will form an edge. This is an edge. If I can get from H to G by multiplying with a generator of S. Okay, so this is an edge. If there exists some element in the generating set such that I can get from G to H by multiplying with some generator, or the other way around. So this is how we will see our group as a metric space by looking at this graph. Okay, so far, so that's why we will use the following metric. Given a simple or simplicial graph, gamma. So here V is the vertex set, and the set of edges, I will consider D to be an ordered pairs. Unordered pairs. So the edges have no direction. We can consider a distance on the vertex set of gamma. So there's this distance on the vertex set, which is the minimum of the length of paths joining these 2 points. So I have 2 points, X and Y. I can consider the distance between them to be the minimum of the length. I will assume this graph to be connected, otherwise this distance can be infinite connected. I will consider it to be the minimum of the lengths of paths joining X to Y. So let's see some examples. Okay, so now we apply this to our groups and we can get metric spaces. So given a finitely generated group, G, and some symmetric finite generating set, S, we can define a metric space. So J is this JS, we make it correspond the Cayley graph. So this is a graph, and this is connected because S is a generating set, and then this induces a metric. So the S is going to be the metric in G corresponding to the Cayley graph. Okay, so to be more clear, what is this distance here? So the distance is defined on G, and the distance from one element of the group G to an element H is the word length of this multiplication. So this is the word length of this multiplication. This means what is the minimum number of generators I need to express this, this element of the group. So in other words, it is the minimum of the minimum number of generators that I need to go from H to G. Okay. So far, this is a bit abstract maybe. Let's see some examples. So the idea is, the geometric idea is I have some element in my group G, which I see as a point, as a vertex. I want to go to G. So I consider all possible paths between them. Okay, so what is an edge here? An edge is a multiplication by some S1 in the, by some element in the finite generating set. So every time I travel through an edge, I'm multiplying by a generator. So this path means that this point here is HS1, this point is HS1S2, and so on. So that G in the end is written as HS1, S2, S6. Okay. So let's see some concrete examples. One of my favorite finitely generated groups is the integers. So first example, the integers. I will take this at my group, and I need to choose some finite generating set. So let's choose the most obvious one, but I need it to be symmetric, so I will also include its opposite. So then what is the Cayley graph? Again, the vertices of the graph are the elements of the group, and two elements are joined by an edge if I can go from one to the other just by multiplying with some generator. In this sense, these are the generators, so I can only join adjacent integer numbers, consecutive numbers. So you can see this graph here is a by infinite ray. Okay, so far, if there any question, please feel free to interrupt me. So now from a group, I have some metric space. This metric space turns out to be a subspace of the real line. It's the same distances as with the real numbers. So, and what happens if we look at this space from infinitely far away? So now I would like you to imagine that you're looking at a blackboard physically, and then you are getting more and more far away from the blackboard. So what your eyes will see is that these points here are getting closer. So if I'm far away from the blackboard, these points start to look closer and closer. And I can take this process to a limit. In the limit, it turns out that these integers numbers, they look like the real line. Okay, so in the limit, I get a continuous real line. So it seems that from far away, the integers and the real line are equivalent. So let's keep this motivation in mind. And another example is set 2. So the integers squared. And some generator set I can choose here is some canonical basis. But then I have to make it symmetric, so I also add the opposites. So here E1 is 1, 0, E2 is 0, 1. So again, the elements of the Cayley graph are the points of the group. So let's say this is 0, 0, 1, 0, 2, 0, and so on. So what if I use this generator? By using E1, by using this generator, I can join every pair of horizontally consecutive points. So something like this. And if I use the other generator, I will end up joining every pair of consecutive vertical points, like this. In the end, I'm left with some grid. So in the end, this is the space we're looking at, or the graph rather. And now we do the same mental exercise. We look at the space from far away. So what we see is that these holes here become smaller and smaller. And so it starts looking like something like this. Right, so in the end, from far away, Z square looks like a plane, looks like the Euclidean plane. So far, so good. More examples. Let's now consider something different. Let's put some torsion inside. So now I have this finitely generated group. And as a set of generators, I can then choose plus minus E1 and E2, where here E1 again is 1, 0, and E2 is 0, 1. So here, this one here satisfies this equation. Here's this torsion. So now the Cayley graph looks like this. So we consider a line here, line. And so horizontally consecutive points are joined by horizontally consecutive points are joined by the first generator, while the other generator is joining those. So this looks like some staircase. What if we look at this space from infinitely far away? Again, we do the same exercise. So this is what we start seeing. So it gets smaller. This difference between the two lines is narrow, more narrow. And in the end, again, this looks like a real line. So you can already guess that these two spaces are equivalent from far away. Okay. Now, something maybe more interesting is what if we look at a bounded space? Or yeah, so in general, every bounded space will look like a point. So if I consider this finite group, for example, set modulo 5, and then this generator, then the Cayley graph looks something like this. There is the class of 0, class of 1, class of 2, class of 3, class of 4, and then the generator is joining these two together. So if I look to it from far away, it looks like a point. Or if I am far away from the blackboard, this collapses to a point. I could also change the generating set. Say I choose this one, plus minus 1, plus minus 2, and then the Cayley graph would look something like this. Okay. But again, from far away, this looks like a point. Okay, so in general, if G is finite, it looks like a point from far away, which is not surprising. Mm-hmm. So far, is there any question? Okay. And a last example, and then we will formalize this phenomenon. One last example is the free groups on more than one generator. So let's consider now the free group on two generators, let's say generated by two symbols, A and B. So the elements are these reduced words in these two symbols. You can also see this as the free product of two copies of set. And then as finite generating set, I will choose this free generators, but again, I need to do this symmetric. So I also add the inverses. So, okay, how can we now think of this Cayley graph? Well, this Cayley graph now, we'll start with a point. Let's say we start with the identity or the empty word. We can multiply by A. Yeah. So if we start with the identity element, I can multiply by A, and then I will get this. I can multiply by A squared, and then I can multiply again by A, or I could multiply by B. I could from A multiply, and then I get AV. So in general, you see, if I multiply by A, I will go in this direction. For example, if I multiply by B, I will go in this other direction. So there is some problem here with this representation, and it's the following. And so say now that I want to multiply from here. So I'm here now, I want to multiply by A minus 1. So I would go like this to get the word AV A minus 1. But now say that I'm here in B and I want to multiply by A. So according to this way of representing the Cayley graph, I should then, yeah, it doesn't fit, right? So I should then get here something like BA. So these two are clashing together. These two are clashing together if I try to respect those distances. So what we usually find in the literature to represent this Cayley graph is the following. We are shortening these edges. So the further away I move, the shorter these edges will look. So here's what we usually do. I start with the identity element. In horizontal lines, I will move in the direction of A or its inverse. In vertical lines, I will move in the direction of B or its inverse. So now what we do is, we repeat every time. So I can, not like this, yeah. So now we repeat the same pattern everywhere, but we shorten the edges. So they're shorter and shorter every time. We also repeat this here. And so on. So this representation can be confusing at first, and this process goes to infinity. So why can this representation be misleading? Well, because these distances are not respected. So I am representing a graph inside a plane, but the distances in the graph are not the same as that of the plane. What do I mean by that? So here I am in one. Yep. Here is one. Here I can have A, AV. If I can draw it. Yeah. So if I'm, no. So here is A, then I can go to AV here. Then I can go to AVA and so on. So if of these edges have length 1, so this edge here looks bigger than this one, but it is not the case. They all have the same length. It's 1. So just, I want to, so this is usually misleading. This graph is not, this representation of the graph is not respected distances. Okay. Is this clear? Are there any questions so far? Curiosities? Please, I'm happy to answer questions. Okay. So then, if not, I will move on. And I want to talk about quasi-isometries, which are the equivalences that are going to represent this idea of looking the same from infinitely far away. Okay. So I will need some definition now. We have a map between metric spaces. So we want to define what it means for this map to be a quasi-isometry. It's a way of saying that X and Y are the same from far away. So we need some definitions. We want to say what it means for F to be a quasi-isometric embedding, but in a weaker sense. So again, we look at F from far away, so we will define the following. Let C be a positive constant and be a non-negative constant. So then F is said to be a quasi-isometric embedding, if the following inequalities hold. So yeah, let me be more explicit. I need to control the distance between images of points. So I want to have control over this distance here. So I don't want the images to be too far away if the points are close. So that I will control here. C times the distance between the points plus some constant. But I also want some properness. So if x is going to infinity, I want f of x to go to infinity as well in a controlled way. So that I will measure with this inequality. Okay. So this is a CV quasi-isometric embedding, and yeah, and then F is a quasi-isometric embedding. And I will just write QI embedding if such C and B exist. So if it is a CV quasi-isometric embedding for big enough constant C and B. Okay. Now I need to formalize what it means for two maps to look the same from far away. And this brings us to the notion of closeness. So the notion of closeness is as follows. Let F and F prime be, I will actually use a different notation. Let F1, F2 be two maps from X to Y. So then F1, F2 are said to be close to each other or have finite distance if there exists some constant which dominates the difference between the two of them. So the distance between them, sorry. So it's the supremum distance between them is finite. That's the same thing. So this is what it means for them to look the same from far away. And now we repeat some ideas from homotopy. So we want to define again what is an equivalence. So F from X to Y is a quasi-isometry. And I will just write QI in uppercase if it is a quasi-isometric embedding and it admits another quasi-symmetric embedding in the opposite direction, such that it's a quasi-inverse, right? So we want to say that F has some inverse from far away. So we would normally say something like this. So the composition of F with G is the identity on X, and Fg is the identity on Y. But again, we want this to happen only from far away. So instead of equality, we will ask for closeness. Okay, so this should remind you of homotopy theory. If you're familiar with these notions of homotopy, then two maps, if I have continuous map F in top, so F is a continuous map. When you want homotopy inverse, you ask these identities here, right? So you want some G from Y to X, also continuous, such that the compositions are homotopic to the identities. So this is a very similar idea, but from far away. It's a different context, but the ideas are very similar. Okay. So again, with spaces, we would say that two spaces are homotopy equivalent if there is a homotopy equivalence between them. Now we will say that X and Y are quasi-symmetric, and I will write this to say that they are quasi-symmetric if there exists a quasi-symmetry between them. Okay. So, yeah, so far, no questions. Okay, so then we will look at the previous examples then. So it turns out that, let's review some examples here. Yeah, as before, some examples. So I will start with Z again as the group, and S is going to be my generating Z plus minus 1. So then this inclusion map, the inclusion map from Z to the real line is a quasi-isometry. This is a quasi-isometry. What would be a quasi-isometry inverse? What would be the quasi-inverse from far away? So a quasi-inverse can be seen to be the floor function. So we send every real number to its floor function, and yeah, you can check F here is a 1, 0 quasi-symmetric embedding. G is a 1, 2 quasi-symmetric embedding. And yeah, so GF is actually the identity on Z, right? So if I take the floor function of an integer, I'm left with the same. And this is, of course, close to the identity, while FG is not the identity, but it's very close. It's close to the identity on the real line. So yeah, this proves that Z and the real line are quasi-symmetric. Okay. More examples. You can use similar ideas, very similar ideas, to show that the inclusion of Z squared to the Euclidean plane is also a quasi-symmetry. In general, And in general, set n is quasi-symmetric to the Euclidean n space. Okay. What else? If this, so we had this example where set modulo 5 was equivalent to a point, and in general, a group G, a finite generated group G, is quasi-symmetric to a point if and only if G is finite. So finiteness is a quasi-symmetric invariant. Okay, so finiteness of finitely generated groups is a QI or geometric property. Okay. We also had this other example where we also had this example G set times some torsion group. And yeah, this one you can check here that if we send set inside set 0, so this inclusion map, which is going to be a quasi-symmetry. Yeah, in general, multiplying, taking the direct product with a finite group doesn't change the quasi-symmetry type. This other space, this free group on two generators is different. If we look at it from far away, it's not in the previous list. It's not quasi-symmetric to any of the previous lists. Okay, so we will go back to this example afterwards. Yep. And something that should worry us is dependent on the generator, right? Deal with that. Something that should worry us, dependence of this metric generate. So I have a finitely generated group, and I want to associate with a finitely generated group. I want to associate it with a metric. So the way I do it is I choose a finite generating set, the Kelly graph, then this distance. So here some choice. So this metric here.
Hello.
Yeah.
Your voice got very low, I guess, at least for me.
Yes,
Yeah, it
it is
got
for
very.
me as well. Yeah.
Yeah. Is it better now?
Yes.
Yeah. Please interrupt me again if it happens. Thank you. Okay. So yeah, so we have this pipeline on how to induce a metric space from a finite generated group, but it's not canonical. So let's see some example on how this can affect the space. We like this example set. Is can you hear me now from here?
Yes.
Great. So I can now choose some different systems of generators. So the easiest one, and the one I chose earlier, was this plus minus one. And then this becomes a by infinite ray. So this could be the Cayley graph. So there's 0, 1, 2, 3. And the distances are exactly what would you expect. So for example, the distance between 0 and 1 is 1. It's the same as always. But we can change the generating set. Right? So now this is one thing. Yeah. I can now also consider the same group with a different generating set S prime. Let's say I will take two coprime numbers, for example, 2 and 3, but then I have to make it symmetric. So I also take their opposites. So actually, let me go onto a new page. Yep, I will go here. So now the group is the same. And I take as a set of generators plus minus 2 plus minus 3. So now I have this sequence again, minus 2, minus 1, 0, 1, 2, but my edges change. Now the vertex set is the same, but it's not the same graph, right? So this goes to infinity, this goes on. So so the edges corresponding to plus minus 2, I will draw them in green. So 0 is connected to 2 and to minus 2 and so on. 1 is connected to 3, 2 is connected to 4, minus 1 is connected to 1, yeah, and so on, like so. And well, if I use the other generator, plus minus 3, I jump in distance 3, or what would be usually distance 3, but now this is distance 1, right? So from 1, I go to 4, from 2, I would go to 5, and so on. So from minus 2, I go to 1, from 0, I would go to minus 3, from minus 1, I would go to minus 1. So this is now what this, oh, I'm missing this one, right? Okay, yeah. So now you see how the distances change. So the distance with respect to S prime between 0 and 3 is 1. Right? This could be weird, but it's just what it is in the graph. And the distance between 0 and 1, well, there is not an edge between them. Okay, so there is no edge between them, so it's greater than 1. The distance is greater than 1. But there is a path of length 2 between them. Right? So I can use plus minus 3 to go from 0 to 3, and then the other generator to go back to 1. This path has length 2. So the distance is at most 2. Okay, so because there was no edge between them, it was greater than 1. Because there is a 2 path between them, it was at most 2. So it is equal to 2. Okay. So this is a mess, right? What if we are doing geometry with, I want to do geometry with my group, but it seems to depend on the set of generators. Well, it doesn't. We're going to do geometry from far away. And in this regard, the generating set will not be important. So this brings us close to the topic, which is coarse geometry. Yeah, there is this proposition, theorem, or whatever. There's this proposition. Let's take care of this. Let G be a finitely generated group, and S prime, two different finite symmetric, so I add the inverses if they're not there, generating sets. Then this map, then the identity, and I will quote that, the identity in G is a quasi-isometry between the two metrics. So on one side, I will consider G with the distance induced by S prime, and in the other side, I will consider the distance induced by S. So I quote here identity because it is the identity on the underlying set, but I'm considering here two different metric spaces. Okay, so this F here is going to be a quasi-symmetry. So that's why if we're defining an invariant, a geometric invariant of groups, it doesn't matter which generating set we take for that. As an example, I don't plan to include many proofs in this course, but I think this is something we can do now. So yeah, so what is the idea behind this? Well, we just use that these two generating sets are finite. So for every S prime, oops, yeah, given S prime in S primes, so since S is a generating set, I can write this element of the group as a product of elements of S. So we can write S prime as a product of elements of S. How many? Well, it depends on S prime. For some S1, sorry about that, yeah. For some S1, S2, Sk of S prime in S. So every element of S prime, I write this as a product of elements of S. So the thing is, since S prime is finite, I can take the maximum of this K. So let M or M1 be a natural number such that K of S prime, I can take the maximum if I want. So K of S prime is at most M1 for every S prime in S prime. I can do this because this S prime here is finite. So what we did do, we wrote every element of S prime as a product of at most M1 elements of S. So now let G be any arbitrary element in the group. Let me do this thing separately. Let G be any element in the group. Consider K to be the distance from the identity to G. So this means that I can, this is the minimal number, the distance in S. No, I want to do this in S prime. Yeah, I want to do this in S prime. Oh. Okay, so this means that K is the minimal number such that G is written as some S1 prime, Sk prime with Si prime in S prime. So now each of those is written as a product of at most M1 elements of S. Then G is written as a product of at most K times M1 elements of S. So this means that the distance from 1 to J, so to G, sorry, in S is at most M1 times K. But I remember here that K was the distance between S prime, between 1 and G in S prime. So now for arbitrary, G and H in my group, this distance here, this inequality is also satisfied. Why? Well, turns out that this distance is the number of elements I need to go from H to G in my generating set S. So it also is the same as the distance from 1 to G inverse H. So then I can use this inequality here. Okay. So yeah, and I will, so this is the quality we need. This is the inequality we were looking for. You can see that if we change the roles of S and S prime, we can prove a similar inequality. So in the end, I also get something like this, 1 over M2, distance in S prime between them is less than or equal than the distance in S from G to H, which is at most, and 1 distance in S prime from G to H. So you can see here, I can take M to be the maximum. If M is the maximum of M1, M2, I can see that F is an M0 quasi-symmetric embedding. Okay, so because of these two inequalities here, we got that F is a quasi-symmetric embedding. So now by exchanging the roles of S and S prime, we can also prove that F minus 1, so it's also the identity, but now I change the order of the generators, is also a quasi-symmetric embedding. Now, since I have these equations, these both are the identities, so they're also close to the identities. It turns out that it is quasi-symmetry. Okay? Yeah, so yeah, that's why it doesn't matter which generating set we take. Okay, we have time for, yeah, we have time for questions.
If you have like some more, like, yeah, you have around 5 minutes more, or since we started late, you have 10 minutes, I believe.
Can you repeat that, sorry?
No, you have 10 minutes still in your hand, so.
Oh, great. So then I will introduce something else here. Yeah, then I will go on. If there is no question, I will move on. I said I was going to go back to the free group. As a curiosity, I want to say something here. Free groups. And their quasi-symmetry type. This is an example. So let's consider a finite rank free group. So again, F1 could be just set, right? So this is a free group on one generator. This is the set. Okay. Now F2 is a finite rank free group on two generators. And so in general, Fn can be seen as a free group on n generators, so as a free product of n copies of set. So how do we compare these groups with respect to quasi-symmetries? Right, so now we want to look at these groups from far away and compare them. We can already tell from our, if you remember this Cayley graph, right? So we can already tell intuitively that these two groups do not look the same. Okay. So, but we still have this question for greater n. Right? So what will happen is the following: F1 is not, again, this is not quasi-symmetric to F2, but then F2 is going to be quasi-symmetric to Fn for every n greater than 1. So if it is at most of rank 2, then it's already quasi-symmetric to F2. How can we visualize this? Let's use an example. The proof is involved, and we're probably not going to cover it, but you can already see something intuitively here, right? So let's go with F3. So now F3, I have 3 generators. I choose a finite generating set. It's going to be the most obvious one. I take the 3 generators and their inverses. And so instead of the previous line, we will have the following, right? So I can now move in the direction of A. I could move in the direction of B. And I could move in the direction of C. So here I could reach A, B, and C. But now from there, I can multiply by more elements. So this pattern repeats itself infinitely, right? And on each of these branches, I keep repeating the same pattern over and over again. So it will take me forever to build some more iterations of this, but you can already imagine how this looks like if we draw it to infinity. So it turns out that from far away, this space looks like a Cantor set. So in this sense, from far away, both F3 and F2, it's like some Cantor set, not with the topology of the Cantor set because it is compact, but they look the same. They look the same. So what is this telling us? It is telling us that this rank is not a quasi-symmetric invariant. So the rank of a group G, so this is the minimum number of generators a finite generating set admits. Yeah. This is an algebraic property, but it is not a geometric property. Okay, so this is not a geometric property. So it is not something you would study in coarse geometry or in geometric group theory. Why? Well, because again, these two spaces, they look the same as metric spaces from far away, but their rank are different. The rank is different. Okay, so this is one example I wanted to see. I have some exercise for you. So since you're not asking many questions, I like to share
So,
some. Yeah.
may I ask one question here?
Yes, please.
Yeah, and it's not a question, it's rather comment. I was kind of thinking when you said this F3, if you go up a little bit, the way you drew the picture, so that is, as I said, that is that looks like Cantor set. So so essentially, what I think, if you write down the Cantor set with ternary expression, then there is a canonical bijection between this set and that set, something like that, or as you said, like topologically they cannot be same. So, or you have you have anything else in your mind when you said these two sets are set?
So I am being very, it's a good question, and it's a sign that I'm being very imprecise here. So what do I mean by a Cantor set? Let me go back a few pages. It's not a proof that they're the same. It's just some intuition, right? So let me go back to this example. I have two generators. So I will keep branching this part here. So if I keep branching on and on forever, I can now look at how many ways do I have to go to infinity in this space. Or I can think of some ideal boundary at infinity which represent the connected components of infinity. And this is something called the end space. Okay, so an end is a way of going to infinity. You can consider an end to be an equivalence class of rays under some equivalence.
Yes.
So this, what is array here is you're choosing a reduced infinite word. So array here is, first I choose A. It has to be an infinite reduced word. So I cannot backtrack again. I cannot go back, okay? I cannot go back. I need to go either on one of these three directions. I need to choose one of them. And it's the same every time. Let's say I choose this one, right? So I'm now here. So again, I can never backtrack. This is not allowed. It has to be a reduced infinite word. So if I go like this forever, this is how I could classify all possible ends. And if you put all of these classes together, the boundary at infinity, oops, sorry about that. Imagine that this is a square. Wow. Yeah, some square here. So the boundary at infinity is a subset of this square, and this is the end space. This end space is homeomorphic to a Cantor set. So it is not the Cayley graph that looks like a Cantor set, but it's rather its end space.
Okay.
And
Yeah.
yeah, by observing that the same happens here. So now, yeah, maybe I draw it like an hexagon, but in the end, it's again, the end space will be homeomorphic to a Cantor set. And it is not a proof that these two groups are quasi-symmetric. You can have non-quasi-symmetric groups with the same end space, but it's some intuition at least, right? So it gives you some intuition
Yeah.
that they
Yeah.
might be the same. Yeah.
Thank you.
It's a very good question. Thanks. If you're interested in, I have some program, so I have some specific plan to follow these next talks. But if you're interested in end spaces or so, I can also make time for that. I can adapt a bit. Yeah. Are there more questions? Okay, so if there are no questions, I will leave some open question myself for those who are interested. Is the following: if someone was to practice, consider, this is a question, the group G of isometries of the integers with the usual distance. Okay, so distance preserving bijections. Then find a finite generating set G. Draw the Cayley graph and recognize its quasi-symmetry type. Okay, so you're given a group, so it's isometries with composition. This exercise consists of finding first a generating set, you symmetrize it, you represent the Cayley graph, and then you can compare this graph with something you have already seen. So you can recognize which space is it quasi-symmetric to. Okay, so if you also this is called the infinite dihedral group. Okay. I think we're already, yeah, it's already time. So I would say that if there are no questions, we can stop here.
Okay. So just for the formality, are there any other questions for Sergio?
Yes, I'm looking forward to it.
Okay. So if not, then let's thank Sergio, and we'll meet again on Wednesday at the same time. Okay. See you next week.
Thank you, Sergio.
Bye.
It's a nice talk.
Oh, thank you very much. I hope you enjoyed. And if you maybe you don't have questions now, but if you think of it during the week, you can send a line to me or also ask it next time. I'm happy to discuss them.
Thank you.
Okay. Bye.
See you. Thank you.